Hello guys, welcome back to another episode of Charles Luke Tries to Explain. Today we're going to be attempting to explain tries. When you do a quick Google search, you might find that a try is an attempt or effort to do something. And unfortunately, in computer science, it's a little different. In computer science, a try is a tree-based data structure, also called a prefix tree. It comes from the word retrieval. It's really common for sorting collections of strings, specifically things like words, IPs, etc., for efficient search, insertion, deletion, and prefix search. So what does a try look like? A try has a root, which branches out to other nodes which contain letter information. From those characters of information, it further branches out into more and more nodes until it hits leaf nodes. Notice how the leaf nodes here are highlighted green. This is to signal a termination of a word. So the way it stores something is, let's say in this try, it stores the word pie. Branching down from root, we can see that it contains P, I, and then E. So this try has the word pie. It's really similar to, a good analogy is Google search autocomplete. When you search the letter H in your Google search engine bar, you might get a couple results like Halloween decorations, holiday gift ideas, anything common, anything probably in your search history. But then when you type in another letter, it gets more specific. It updates those recommendations. Oh shoot, my search history. But it updates those recommendations based off of the new updated prefix. It finds the validity. So how does insertion work for a try? So starting from your root, let's say we're trying to insert the word band, B-A-N-D. Start from the root, look at B, B exists, traverse to A exists, traverse to N exists, and finally we find that the letter for D doesn't exist. So we append that on, B-A-N-D. We then need to update that as the new terminator and change our old one to not be a terminator of a word. This is O of L time complexity, where L is the number of characters in the inserted string, because you need to compare every single character in your string that you're inserting in order to find out where it's going to end up. For searching, it's really similar to the pie example I was showing earlier. Let's say we're searching for the word pen. We traverse down and see that P does exist, E does exist, and N does exist. And also, it ends on a word terminator, denoted by the green and the leaf node. So this shows that this will return true. Pen does exist. This is also, so what happens if you can't find a word? The word that you're searching for doesn't exist. Well, let's say we search for per. We go to P, E, and then we find that, okay, where's R? R doesn't exist, so this will return false. The time complexity of this is also O of L, where L is the number of characters in the string. This is because in worst case scenario, you need to compare every single character in your string in order to find that yes, it does in fact exist, or maybe it doesn't, on the final character. There's also an operation called prefix search. Sometimes you don't necessarily need to search for a whole word, you just want to know if a partial word or a prefix exists. For example, the prefix ban in this case, of band, B-A-N, B-A-N-D. We can find that B, A, and N all exist, but now we don't need to check if it's a word terminator, if it's a leaf node. So this is kind of a generalization of the search algorithm. This is still O of N, because the worst case scenario, we need to check every single character in the string to figure out if it does exist in the try. So what are some pros and cons of tries? Something you've probably definitely seen from my past explanation is that all operations are O of L time, and this can be really helpful. Based on your length of your inputted string, which often isn't too long, you can get a quick result. It's also really good with sorted related stuff, printing things in alphabetical order, looking at this kind of structure, specifically that you've probably seen in our autocomplete and autocomplete example. It's also less space than a binary search tree. In a binary search tree, if you were to insert the same words, band, banner, something all starting with the same prefix, you need a new node for every word. But in a trie, you just need a couple of branches from one prefix section. And finally, there's no hash function, so it spares a lot of the time and struggle of implementing a good hash function that comes when you use a hash table. Some cons, however, are that it uses a lot of memory. There's a ton of pointers per node. They're not necessarily binary. For the word insertion case, each node could have up to 26 letters, and if you're doing things like numbers, ASCII, that could be even more. That's a lot of pointers coming out of each node. And a good hash table, which can do all of this in O, all the operations in O one time, might just be a lot better, if you can get it, of course. So what are some applications? We've shown earlier that this can be used for autocomplete, for looking at prefixes, matching that to current words, seeing if that exists in a database, and it can also be used for IP routing and networking, looking at sections, the starting sections of IPs to match that with necessary ports. Now let's hop into a live coding demonstration. So how does a trie look like in practice? There's some libraries out there, but if you want to implement it yourself, you need a trie node with children, in this case 26, but however many you would need for every node. In this case, it's the number of letters in the alphabet, because we're doing word insertion. There's also an isLeaf, which demonstrates the whether it's a leaf or not, which is highlighted green in our visual aid. When you create a node, you want to set all the leaves to false, because it's not a leaf node yet, and all the children to null pointer, of course. No memory leaks today. For insertion, you want to look at the key, compare that to the starting key, and then attach that as necessary. I won't go through all of the details. This is something you can look at and try to code yourself when you're implementing. For searching, you want to implement the same sort of structure that I showed in the slideshow, same for isPrefix, and you'd want to return true or false as necessary. Alright, so let's see how we can use some of these functions in our trie. So for any trie, you need to make a root. And this is crucial because that's how you're going to be able to branch out to all the other nodes. This is the dummy root, dummy node in the beginning. And we'll also need, let's test insertion first. So let's make up some random words. Sure, okay. Ben, band, banner, do, dot. Now, if we iterate across the vector of strings, and we can test our insertion. Boom, run. And it runs successfully, but insert is a void function, so this won't really show anything. Now let's test our search. In fact, let me copy this over. Just change this to search array. Now we're searching in the array to see if all of these same words have been successfully inserted. So this should return all true. Or if I change this, one moment. And now we're going to call our search function. And note that search returns a boolean, so we want to test for that, which I totally forgot a second ago. Okay, boom. Let's test this. All true. So all of these have been successfully inserted. But how can you guys know for sure that I'm not just making a shoe printer? So let's change some of these to ones that aren't in here. Let's say band or don't and do. So Ben and do are both in there, and these two aren't. So it'll be true, false, false, true is the expected output. And we can see that's exactly what we get. So that's how you would use search. Now what about prefix search? Prefix search. Well, prefix search, maybe if we search Ben or B and do, these two should both exist. But what if we do something like don't again, or hi? Both of these prefixes should exist. We can call our isPrefix function. And let me comment these out so it doesn't get confusing. Sorry, I've been coding in Python a little bit. As you can see, yes, this is exactly what we expect. True, true, false, false. So that's kind of how you would use the functions that come with the try. Thank you for your attention, and I hope you learned a little bit more about tries today.